Okay, so welcome to Robotics 1. In today's class, what I would like to do is, I would like to kind of show you the demonstration of how image acquisition works with MATLAB. And then we can kind of spend some time on looking at different algorithms. So what I have here is I have a small webcam, and you don't need to have the webcam. You can use something else. That's totally fine. So I will show you the setup that I have. So I want you to see my setup. I have a small webcam, and then at the bottom of this webcam, I have a small servo. And this webcam, if you look from top, it is looking at a grid. So I want you to see, let me show you what everyone is saying. So this is what is saying, everyone is saying. So what we have is, we have a webcam that is looking down, and then here at the bottom, we have a small servo. Now this webcam is going to capture an image. And as you can see, this image has this grid. This grid is in the world coordinate frame. What we want to do is, we want to correspond this grid to the pixelated image. So what we are going to do is, we are going to use a simple MATLAB script. And I want you to run this MATLAB script on your MATLAB. And then we can talk about the conversion between pixels and conversion between the images. So with that, I want you to go to MATLAB. And in MATLAB, what you will see is, I want you to go to Simulink. In Simulink, go to library browser and then look up image and search. So you will get this image processing toolbox. And if you have done the project, probably you are familiar with some of these options. But if you have not done the project, I would strongly recommend you to do this exercise. Then here you will see that there is an image acquisition. Can you see this image acquisition from the video device? Drag and drop that into the canvas. Grab that block and drag that into canvas. So this is the Simulink canvas. That is where you will draw it. And I want you to double click on it. Now, unfortunately, this gives me an error, because since I'm using Zoom, all my graphic resources are utilized by Zoom, but you should not get this error. You will get a dialog box, and it will ask you to install the drivers. So if you don't have the drivers, what I want you to do is, if you don't have the drivers, please go to MATLAB and download these drivers. Image acquisition toolbox support packages for generic video interface. So basically, these drivers you will have to download. Once you download these drivers, what you can do is, once these drivers are installed, MATLAB should be able to acquire the image from your webcam, image from your USB cam, and so on. Were you able to see where these drivers are? Can you get these installed? Okay. Once this is done, what? You found it? Okay. So then I want you to go to USB PC camera, double click, and then it gives me an error, but it will not give you an error. It should open this dialog box. Is it opening this dialog box? And in this dialog box, it will give you an option. Since I have two cameras attached, I have a webcam, which is the FaceTime camera, and I have the USB cam, which is the bottom looking camera. You will get, if you have a camera then you will get one option. Are you with me so far? Are you getting that option? Please click on that option. So please click on that option. And here it's going to give me an error because I'm using Zoom. And then what I want you to do is, I want you to look at the video format. Depending upon the camera that you have, you will have an RGB video format, or you will have Y2 video format, and that is the pixel location. So you can get an image which is 640 by 480. You can get an image 160 by 120. You can get an image 176 by 144. What I want you to do is, I just want, if you have HD camera, then you'll probably get 1200 by 640 or some big image. Then I want you to click on preview. I want you to click on preview. Are you able to see the image? So once you click on preview, you should be able to see the image. And then what you should do is, you should go to data type, and in data type, it will actually give you an option of how to pass that data. So basically, you can get the components of that data, for an example, Y, CB, and CR, and plot those with something called as the video viewer. Are you with me so far? So this option you will get in library browser, image processing toolbox, and you will see here all these different functions that we talked about. So you will see something called as edge detection, histogram equalization, auto thresholding, image complement, demosaic, fur filter, and so on and so forth. So once you get an image, what you can do is, you can feed that image to this block, and that will show you the image. So you can see the image. Then what you can do is, you can actually separate the image into its different constituent parts. For an example, Y, CB, and CR. Out of these, if you want to pass it on to something called as auto thresholder, which means you will take the color image, pass it through the threshold, and then convert that image into a black and white binary image. So please grab that auto threshold block, feed that image, the auto threshold, and then plot the black and white image. Are you with me so far? This image you will get in library browser. So you can see there is this auto threshold. This will actually take a color image and convert that into a black and white image. I means color image. And once you attach the threshold, depending upon whether you're above or below threshold, that pixel will be denoted as 1 or 0, black or white, and you will get a black and white image. Now, what I want you to do is, I also want you to look at this two-dimensional fur filter. Two-dimensional fur filter is a low-pass filtering that will actually take out the noise from the picture. So I want you to grab that block, place it, and see the image, what happens after fur filtering. And it's very easy to see. You can take an object, maybe a circular object, place that object in front of the camera, and you'd be able to see the difference between the color image, the image components, then after filtering, what happens, and then after thresholding, you will be able to see a black and white image. Now, the next step, which I want to show you here, and this will not work on my computer because I don't have access to my video camera, but I want you to go to blob analysis. So blob analysis is some type of pattern recognition. Say, for an example, if I have a circular object, the circular object is in the field of view. I want to detect that circular object then I can actually do the blob detection and it will actually find out where that blob is. And then I can estimate the area of the blob, bounding blob, major axis, minor axis, and you can look at the centroid. So this actually, once you click on the centroid, this blob is going to give me here the location of the centroid. Are you with me so far? So this location of the centroid is X pixel and Y pixel location of the centroid of the circular object. Are you able to do it? Any questions here? And then this display will give you the X pixel and Y pixel of that circular object. And that will be your X and Y location that can feed for the inverse kinematics of your robot. And then if you have another script, you have to actually get this X and Y from here. And then you can run that through this script wherein your servo is controlled by the particular joint angle. What you can do is then you can run that and you observe that you can load this on your computer and then you can actually have your servo move. So you can see here the servo that is connected over here. It should be able, you should be able to get it moving.
You want the desk bin?
Yeah. Question?
Sorry, I thought I was muted.
Question?
Oh, no.
So what you can do is you can feed the sine wave or any particular angle that you want. You can actually set up your hardware. I'm using a very simple Arduino Uno. And then just once it is connected, once the COM port is configured, then what we can do is we can actually run this code onto the computer and then basically have the Arduino, or for that matter, any microcontroller run this code. So hardware, and then you will see, you'll just have to go to hardware setting, make sure that you are running this code on Arduino Uno, and then once you click OK, then you should be able to get this session running. So I would encourage you to try to do this exercise. That way you have the image that is captured inside the MATLAB. You analyze the image, then get the relevant data from the image, and then program your microcontroller to send a pulse width signal to the servos, and then your robot can actually go to that position. So this is how basically a simple image-based acquisition works. Any questions? So I will show you the script, and I would strongly encourage you to duplicate that. And once you have the appropriate drivers, this script should work on your computer. The next thing is the output of blob analysis, which means once you detect that circular object, once you find the centroid of that circular object, this blob analysis will give you centroid of the circular object. That centroid will be in terms of pixels. But what I want you to do is, I want you to understand, once you take the snapshot, MATLAB will give you the scale. So what you can do is, if once you capture the image, there is an arrow icon, click on that arrow icon, and basically you can measure the pixel and the length. So you have a scale factor, which means one X pixel is equal to maybe 2 millimeters. One Y pixel maybe is equal to 5 millimeters. So you can convert that pixelated image into the world coordinate frame or in world dimension. That's exactly what you need to do when you are doing the image processing. Everyone understood this? Again, it's not a spectator sport. I would strongly recommend you to play with it. It's very easy. And once you look at the image processing toolbox at MATLAB, all this is very nicely explained in that image processing toolbox. Now, with that, what I want to do is I want to move on to the remaining part of today's lesson. So in last class, we actually talked about why do we need image processing. Image processing is ubiquitous in robot vision. You use the image processing to capture the object, to detect line, and also to perform real-time image processing and decision making. So we looked at what do we mean by image. Image is nothing but a matrix, and that matrix has some values associated with the intensity of that pixel. If it's a black and white image, if it's a purely black and white image, then you are going to have zeros or ones. If it's a color image, then basically you have three components of it, RGB, and every color will have intensity. And when you merge all these three together, then you are going to get that specific color. Now, we looked at the bit. So how do we get the image in bits? Remember, it's a digital image. So the only thing that can be represented is zeros and one. So finally, at the end of the day, we have the image that is encoded as zeros and ones. We looked at the Fourier transform. Fourier transform is a technique wherein you have a signal, a periodic signal. We decompose it into its subcomponent and then use image processing or signal processing techniques to extract the information from that signal. We also talked about the concept of Fourier transform. Fourier transform is nothing but the Fourier series when the limits are stretched to minus infinity to plus infinity, which means a non-periodic signal or a periodic signal, you can use the Fourier transform to analyze. We also talked about the aliasing, which means if you sample it incorrectly, then spurious frequencies or spurious image signals appear from that sampling, and you want to be careful about that. That's why we have something called as a Nyquist criteria. But again, nowadays there is a concept called as compress sensing that allows you to violate Nyquist criteria. If you look at the image is actually a two-dimensional signal wherein you have it's a matrix. You have some value around rows, some values around column. So basically, whatever transform you do, it will be minimum a two-dimensional transform. And then by performing the signal analysis, amplitude thresholding analysis, what you can find out is you can find the pattern, and that would allow you to detect edges, that will allow you to detect shapes, that will allow you to detect the changes, identify the noise, and so on. We also talked about what do we mean by resolution and quantization. So for image processing, with both of these components are very important. Now, sampling theorem, Nyquist criteria we talked about. We also talked about aliasing. We also talked about how does sampling affect the quality of the image. Many a times what you want to do is you want to use the appropriate sampling, because more the sampling, more number of data points you have, more storage requirement, more computational requirement. So for an example, if your just motive is just to get the black and white boundary, then you don't need a color image. You can actually get a low resolution image and still be able to find out the boundary. We also talked about the histograms. So for an example, on the left hand side, the color shades are squashed. On the second hand side, that color shades are mapped over the bigger range so that you get a better representation of the image. If you want to manipulate the brightness, contrast, again, what you do is you can either use a mask or you can use some type of a simple signal manipulation, and you got images would become brighten, or your images will have contrast. Now, I just want to tell you what that means is you have the exact same image, but what I want you to do is I want you to look at the histogram representation. So you have the original image. If I were to spread this histogram, I get more contrast. If I were to shrink it a little bit, then I would get more brightness. So you can see the median here for the same image, which is brightened, is 166. Median here is 136, and median here is 139. So thresholding is the mechanism wherein you specify a threshold, and if a pixel value is below the threshold, maybe you term it as black. If the pixel value is above the threshold, you call that pixel white. So you can convert a color image into a black and white image, and depending upon your threshold, the image appearance changes. So for example, you have the image on the left hand side. If your threshold is at 100, then I want you to understand this region here is gone. It's completely white. But if you change the threshold to 150, then the image here is termed as the dark or the black image. Now, next part is you can do the multimodal thresholding, which is you can have the image and you can have different thresholds for the different parts of the image, and then you can actually manipulate that image. Again, this is very important if you want to detect the shape. It is very important if you want to recognize a pattern, if you want to recognize a feature, if you want to recognize an edge. So this multimodal thresholding is very, very important. Now, one super important concept in image processing is something called as convolution. And this is very important. Sometimes it is also called as masking. Here is the basic idea. What you have is you have this image, and this image has these pixels A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. There are some pixel values. Now, what I want to do is I want to perform some type of masking operation or some type of convolution operation. So here is what I'm going to do. I'm going to use this matrix M1, M2, M3, M4, M5, M6, M7, M8, M9. So these are all numbers. Some of these numbers could be ones, some of these numbers could be minus ones, some of these numbers could be zero. What I do in convolution, I take this matrix, place it on this first 3 by 3 matrix. I place this matrix on this first 3 by 3 matrix. And then I perform a very simple mathematical operation. A times M1 plus B times M2 plus C times M3 plus E times M4, F times M5, G times M6, and so on. So what I have done is I have taken that mask, I have placed that mask on the image, and I have multiplied the pixel value for that image by the mask that is on top of it. And I sum it for this entire mask and finally normalize it. And basically that normalization result, I would place maybe somewhere at the centroid of the mask. That will help me either get the edges, vertical edges, horizontal edges, or understand the feature. Sometimes this type of masking technique is used for filtering. Please try to understand. This is all discrete data. It is not a continuous data. So you have sort of numbers which are positioned next to each other. So what I do is, by this discrete manipulation, I can either soften the image, I can capture certain features of the image, and this masking operation, or also called as convolution operation, is very, very important in image processing. So you would again, next part is, if you want to find out the connectivity. So to look at the connectivity, how do we know if a line is horizontal, a line is vertical, or line is inclined? So what we do is, we actually grab a pixel, and then we actually see the pixel values around the pixel. For example, you can have +4 -4 connectivity. So you will see the pixel values around that pixel and compare the actual values. You can also go diagonally and then see if those pixels are connected, which means those pixel values are close to each other. You can also choose H6- or V6-6 horizontal pixels, 6 vertical pixels, and see what are the relative values, magnitudes of those pixels. And this sort of comparison will tell you whether we have a horizontal line, whether we have a vertical line, or whether we have an inclined line. And if we want to reduce noise, again, same type of pixelation operation and masking operation is performed, wherein you have a mask and you place that mask. And let me tell you what this mask is going to do. Depending upon what numbers you have, the pixel values will be either average, either magnified, or reduced. And the effect of increasing the individual pixel values, decreasing the pixel values, or changing the relative values of pixel will manipulate the image. Let me tell you, image processing is at the end of the day is, you have this matrix. That matrix has bunch of numbers, and how you manipulate each number identifies the pixel intensity, and how do you manipulate each numerical value to change the appearance of that image. That is all there to it in the image processing. And all the techniques that you will see, they use linear algebra, they use numerical computation, and then maybe you look at different patterns in that matrix, you manipulate the various values in the matrix, and then use that for processing. For an example, there is another concept which is called as neighborhood averaging, when you take the pixels, use a mask, and then change the values so that you get an average image. So you will see original image, you get the corrupted image, you see the 3x3 neighborhood averaging and 5x5 neighborhood averaging, and that would affect the behavior or appearance of that image. Image averaging is used in a lot of applications. If you want to soften an image, you can use image averaging. If you want to highlight certain features of the image, then you can use image averaging. And then if you want to reduce the noise in the image, you can use image averaging. Then there is this concept of median filter. What is the median filter? The median filter is, you got this series of data, you arrange the data from the lowest value to the highest value, and then you pick up the median, which is the value at the center of that time series. And that median filter is used to sort of make that image grainy, and then it actually changes the histogram, and it will change the appearance of the image. And sometimes it is very important when you are recognizing certain patterns, you perform the median filter processing so that that pattern can be recognized from the surrounding. Now, as you can see, this is the effect of median filter. The first image is the original image. Second image is the noise image, and you can see 7x7 median filter. You can see the image that has softened. Now, if you want to do an edge detection is very important because we want to find out the road, we want to find out the path, we want to find out where particular object is. So the line or the edges are very important. There are different techniques for edge detection. Again, we are not going to talk about all of those, but maybe few of those. Some techniques are mathematical, they are based on algorithms. Some techniques are heuristic, which again based on rules, and some techniques are sort of descriptive, where you have a certain description that is encoded as an equation and then that is used. So the way the edge detection is used is, what you want to find out is you want to find out the relative difference between the pixels. So that's why this is where the gradient comes in the picture. Gradient is nothing but the derivative which is in the discrete domain, which is the change around x, change around y. What you can do is you can find out the second order derivative, which is called as Laplacian, and then you can find the first order difference, you can find the second order difference, and that would allow you to find out the relative sort of relationship between adjoining pixels. And this relative relationship is used to find out whether there is an edge or there is no edge. Again, the first derivative equation in the discrete domain is shown over here, which is nothing but a running filter. You can actually do the exact thing, same thing with the second derivative. And then basically at the end of the day, and I want you to understand this, super important, you are gonna get a mask and you are gonna perform the masking operation on that entire image. And once you run that image, run that masking operation on the entire image, basically that will give you the first derivative, second derivatives, and so on. So again, this is a very simple example of convolution using, and there are different techniques. There is Sobel, Roberts, and Prevet, different types of algorithm that are used for edge detection. All these algorithms, yeah.
Those 3x3 masks are derived from using the gradient.
Oh, those 3x3 masks, basically those, okay. There is a lot of discussion that goes behind the Sobel algorithm. So Sobel, Roberts, and Prevet, they are algorithm for edge detection. And these edge detection algorithms, they work on different principles. For an example, one of that algorithm uses gradient. Another algorithm uses gradient and Laplacian. And another algorithm is using a multiple mask that you run. What I want you to understand is it's not straightforward how it's implemented. But if you take an image and if you run this convolution operation on the image, what happens is once you see the result, you will clearly see a pattern in that resulting matrix. So here is, okay, let me explain what this means. Imagine you have an image. This image is bunch of numbers. This image is bunch of numbers. Now we use this mask, and this mask will have numbers, and the mask that is used to detect horizontal line, mask that is used to detect vertical line, mask that can be used to detect inclined line could be different. So for an example, there are some numbers 1, 2, 3, 1, 2, 3, 1, 2, 3. I take this mask, place it over here, find the result of this mask, place that value at the center, take the mask again, move it by 1 pixel, move it by 1 pixel, and when I perform this operation on the entire image, you would see the mask that is designed to detect horizontal line will clearly show you the same values horizontally. So you can actually detect if there is a horizontal line at certain location or not. So for an example, I would look at, if you look at this, again, these are different types of masks. So for an example, Laplacian one mask is derived from the second derivative. Laplacian 2 mask is, I think, rotated by 90 degrees. There is a Sobel mask and there is Robert's edge. So you can see the original image. Then what happens once you apply the Laplacian 1? What happens when you apply the Laplacian 2? What happens when you apply the Sobel's operator? And what happens when you apply the Robert's edge algorithm? So these are all different algorithms. What that will do is, now I want to, this part is not very clear, but let me explain it to you what it means. Once I take that mask and I sequentially perform the convolution operation on that entire image, what is going to happen is the edges will be 1 and the parts that are not edges will be 0. So what's going to happen is the pixels which are here, all of them will be 1, 1, 1, 1, 1, 1. So clearly you can see that there is a 1 and there is this region 0, which means that edge is somewhere over here. That is exactly what that mask does. Everyone understood this? But if that mask is not done properly, then you will not be able to acquire the image. For example, in this particular case, if I use a Laplacian 1 mask, and if I run that mask over the image which is shown in A, I don't see any edges because that is not the right mask. When I use Laplacian 2 mask, I see this difference, black and white difference. So I know that white region is the edge and black region is something in the background. On the other hand, if I use the Sobel operator, Sobel mask, then I see those images as a clear differentiation between the black regions and white edges. Everyone understood this? If you look at the textbook, there are actually examples where he has shown the image and then he did the convolution with the mask, and then you will see that once you apply the convolution, then certain pixel values will go up, remaining pixel values will go down, and the values of the pixels that is rising to up, that is an indication of the edge. And again, there are some heuristic algorithms wherein if you want, you can scan the images based looking at the relative connectivity. So if you see an image, maybe that's very dark, then what you do is you scan the pixels on left, right of that image, the pixel, and then look at the relative intensity, because if it's an edge, then this pixel would be relatively at the same intensity if this is an edge. If this is not an edge, then the relative difference between pixel intensities will be quite high. And then what you do is once you scan, then you can see what regions those are. Then again, if you want to run the filter through an high pass filter, again you have a mask. So basically that is the mask. Once you run that mask onto the image, it's basically performing a high pass filtering of the image, which means all the low frequency content of that image. What do I mean by low frequency? So I need to emphasize what do I mean by low frequency and high frequency in terms of the image. Please understand, image is static, which means once you take a picture, once you take a photo, what you have is you have a matrix. It's not a signal that is time varying. What do I mean by low pass filtering of an image? Low pass filtering of the image means if you have a pixel, if you have another pixel, if they are relatively close to each other, that means they are about the same region. There is no sudden change. In other words, the frequency is low. So once you pass that through the mask, then the pixels which are close to each other will be retained, and the pixels, they have sharp contrast with respect to each other, will be discarded. Yes.
Isn't the distance between each pixel?
No, I mean the magnitude, the intensity of the pixel. So for example, if you have so let me explain what it means. So imagine this is one pixel, and maybe this is the second pixel, and then this is the third pixel. So what you have is you have the intensity of the pixels that are varying at a high magnitude. So this is basically a high frequency content. Otherwise, say you have a horizontal line. So this is one pixel, this is the other pixel, this is the third pixel. These three pixels are next to each other. The intensities are not varying quickly. This means this is a low frequency content. So when I run that through a high pass filter, what do I mean by high pass filter is if there are pixels where relative intensities are very close to each other, they will go away. If I do it through a low pass filtering, wherein the pixels which are next to each other that have significantly different intensities will be filtered.
What do you mean frequency? Does it mean gradient between?
Gradient, correct. So yes, intensity, that is in terms of the gradient. Because please understand, once you take a picture, you have an image. There is no change. But basically, you can high pass and low pass filtering in the case of images is just nothing but manipulation based on the gradient. So difference between pixel intensities, the pixels which are close to each other. Now, this is very important, huge transform. And this transform is basically taking the data in XY plane and transferring that into something called as MC plane. Because understand the equation of the line is y is equal to mx plus c. So every data point that has expressed in x and y can be expressed into slope and y-intercept plane. And then what allows, if once we do this conversion, what we can do is we know that if the pixel is on the same line, then the value for M and C for that pixel is always going to be the same. So the logic is very simple. So what we take is we consider certain pixels and we want to find out whether these pixels are on one line or not. So what we do is we take the pixels XY location and either convert that into R and theta values, or we convert that into a slope and y-intercept values, and then plot those onto theta and R plane or M and C plane. And if all these points, they are at the same point on M and C plane, then we know that that point is on the straight line. Why is it needed? Sometimes what you want to do is you have half of the edge and you want to extend or complete the edge, or you want to find out which points are connected, how they are connected. So huge transform helps us to transform the pixels in huge plane, and then basically once we know that they are connected or they are corresponding to one point in huge plane, we can transform them back and then reconstruct the line. So again, this is the basic algorithm. You have the line, you rewrite the line into C is equal to minus xm plus y, and then convert those x and y points onto the Hughes plane. Now, segmentation is also another technique that is used for image processing and analysis. You basically take the image and convert that into different segments. MATLAB has a very nice toolbox for segmentation. Again, there is a Simulink block that can be used for segmentation. I would strongly encourage you to take an image, feed that through segmentation, and then basically see it yourself. Segmentation will allow you to focus on certain part of the image. Segmentation can be used to find edges, regions, texture, and so on. Again, there are different techniques, mathematical algorithms for segmentation. Again, clustering, there is a mean calculation, reassignment, and so on. Sometimes we have to use the morphological operations, whereas basically you have two different shapes. You add the shapes, subtract the shapes, or perform some operations that are related to the set theory. So that can be used for data reduction, feature extraction, and so on. If you look at the binary morphology, if you want to soften the image, if you want to manipulate the image, if you want to change the shape of the image, sharpness of the image, so you can actually combine multiple shapes together, perform these binary operations of addition and subtraction, and then that will that is how you can manipulate the image. Yeah.
Are you saying that we combine two filters and then do symbol?
No, so what I'm saying is, imagine here you have a sharp line. Okay. What I want to do is I want to soften. So basically, I want to add a fillet. What would be the best way to add a fillet? That is performing a binary operation, morphological operation, which means I have that circle. What I would do is I would combine that circle with the image that I have where there is sudden sharp changes. So grab that, place it over there, and give the resulting image some sort of a fillet. So binary operation is combination of existing image or existing image with some other shape, binary shape. That's what it is. If you want to thicken, you can take an image and basically perform the thickening operation, which is nothing but increasing the intensity of the nearby pixels. That will allow you to either soften the edge or basically make certain features very prominent and so on. Same thing in dilation. What you can do is you can have the connected signals, pixels, and then you can add a layer to the object. And sometimes the dilation would actually change the shape. If you can go to MATLAB, and there is in the Simulink, there is a block that can do the dilation. Erosion is nothing but removing certain part of the pixelated image. So basically, foreground pixels are connected to background pixels that are eliminated. And finally, what you can do is this can be used again to soften the image. That can be used just to convert a picture into sort of a skeleton or a line drawing or line diagram, and that can be used for some other application. You can also do a skeletization, wherein you have the basic image and then you retain the most predominant features, which is in terms of 1 pixel thickness, and then basically you can retain just the skeleton of that image. And again, you can see once you do the skeleton, that bolt, the nut, that get converted into the most primitive shapes that are shown in this image. There are other operations. You have something called as the open operation, close operation, fill operation. Again, these operations are manipulating the pixel values depending upon the connectivity, depending upon different algorithms, and so on. And then when you do the image analysis, you are going to perform recognition, extraction, position analysis, orientation, and so on. And there are different mathematical algorithms that would allow you to perform this type of analysis. And the one example that I showed you, the blob detection, is one of the image recognition analysis algorithm. In what you have is you have a connected region, and depending upon the connected region, you see those pixels, then perform this mathematical operation, and then actually you can find the moments, and then you can find out the centroid. So if you look at the moment equation is nothing but the value of that pixel multiplied by the x value of pixel, x location of the pixel, y location of the pixel, and the intensity of the pixel. And a and b's are the values. So a could be 1, y could be b could be 1, a could be 2, y could be b could be 0. So you can actually find out the moments that are given by MAB, where A stands for the index of X, B stands for index of Y, and you can find the zeroth order moment, first order moment, or second order moment. For an example, the zeroth order moment is nothing but the area. The first order moment is nothing but the moment of area about X. You can find the moment of area about the Y. And then please understand this X bar and Y bar, the center of the area related to the X axis. Similarly, center of the area related to Y axis. That is exactly how that blob algorithm is finding out the centroid of the image. So as you can see, it takes that pixel, it finds the moments, and then divides it by the area. And again, you can go, I have seen going up to the second order, third order image moments, and those can be used for image processing. There are other techniques, which is like you provide a template, the templates get matched with the image. There is something called a discrete Fourier description, and there is a computed tomography. So these are all image processing techniques. There is a nice MATLAB Simulink block for template matching, wherein you can provide a template of an image, and if the similar pattern is found in the image that you have captured, then you can actually get 0 or 1 depending upon how good the match is. If you want to do the depth measurement, you can use some rangefinder like LiDAR, or you can use a stereo camera where you can use a triangulation approach to find out the depth. So the idea is you have two cameras looking at the same image, but clearly, since those two cameras are apart from each other, but they are looking at the same point, you are going to get sort of a triangulation, and that triangulation can be used to find out the depth, and that is the principle of stereo imaging. So again, let me show you, this is how it works with stereo images. You have camera 1, you have camera 2, you capture the image, but please understand, you see the relative difference between the pixels, and then basically use the triangulation to find out where that object is. And sometimes what you do is you can use some specialized lighting. That way what you see is basically the depth is represented as a different shape. For example, this is the shape that is protruding. You have this plane of light. So once this area is illuminated, basically you see the edge. That is an indication that there is a relative elevation between the plane. And again, there are different ways of compressing the images. There is PCM, there is pseudo-random, there is half tuning. Image compression itself is a huge area of research, and there are many mathematical algorithms that can be used for image compression. Because please understand, image processing is a very intensive activity, because you have these pixelated images, you have these matrices and tensors that you have to operate on. That's why these clever mathematical algorithms are used to compress the data. Again, there is this predictive coding and error correcting codes. So for an example, if you have an image, you are transmitting the image, it's a binary transmission. So you don't know if the image that is sent from the send unit, same thing at the receiver end, if the same image is captured. So basically what you do is you add some error correction data, wherein once the image is received at the receiver end, that error correction data can be used to make sure that the image that you have is the correct image. And then again, there is constant area quantization and different techniques that I would encourage you to read. Again, as a roboticist, we are more interested in getting the image, processing the image, and capturing the most relevant information from the image. Again, there is lossless compression, there is lossy compression, and there are different techniques within lossless and lossy compression. The color images, they will have R, B, and G, and then basically these are the matrices. You actually put those on top of each other, and you get the final image. There are different representation schemes and cameras. They depending upon the way the camera hardware is, it can do the RGB or it can do the YCRB or different types of images. Sometimes you use the heuristic wherein you have different rules, different thumb rules, and you can have some type of if, else, then type of statements that can be used to manipulate the images. And with that, we are finished with chapter 11. So this is mostly a theoretical chapter, but please try to understand all the functions that we talked about. They are inside the MATLAB. So I would strongly encourage you to watch the webinar. And I think there is a course that I have asked you to do, the image processing course, wherein they will talk about how to use all these functions for processing images. With that, I'm going to stop here. And if there are any questions, I would be happy to answer. Otherwise, I wish you all a happy Thanksgiving, and I will see you next week. Thank you very much and have a good day.